Mechanical waves. What we have here is some information, some characteristics about a wave, and we want to start putting it together into a nice equation for a wave. And the first thing we're going to do is find the frequency and the angular frequency and the wave number. So for the frequency, one thing we always know about a wave is that the velocity is equal to the wavelength times the frequency. So that tells us that F is v over lambda, and v and lambda were both given to us. So that's pretty straightforward. 40 meters per second over 2 meters. And what do we have? 20 inverse seconds. And we kind of get tired of writing inverse seconds, so we write 20 hertz. 20 cycles per second, or 20 hertz, is the frequency of this wave. Now we often want to use angular frequency. You'll see why in a moment. Oops, that's not part B. The second thing we're looking for is angular frequency, and that's omega. And omega is equal to 2 pi radians times the frequency. So 2 pi f, and the frequency is 20 hertz. So we get 40 pi inverse seconds. And I like to write it as radians per second for the angular frequency. 40 pi radians per second. And the last thing we're looking for is the wave number. That's k. And that is 2 pi radians over the wavelength. So the wavelength in this case was 2 meters. That gives me pi radians per meter for the wave number. The reason we needed all this stuff was because we want to come up with an equation for this wave, right? And for a wave traveling in the plus x direction, we can use this equation, that y as a function of x and t is equal to some amplitude times the cosine of kx minus omega t plus a phase angle. And we could have also used a sine function. We just would get a different phase angle in there. Basically, this phase angle is there to fix the starting condition, right? The initial condition. The condition when both x and t are 0. So you'll see that in just a moment here. Well, let's just do it right now. If x is 0 and t is 0, then what we're left with, our initial condition, is a cosine of our phase angle. And so what is our initial condition? Is it at y equals 0 in our starting place? Is it at a maximum displacement? Where is it? Well, in the problem it says it's at its maximum upward displacement, so its maximum positive value. So that means we want the cosine of our phase angle to be equal to 1. And so that means that our phase angle in this case is going to be equal to 0, because the cosine of 0 is equal to positive 1. And that gives us our maximum displacement when x and t are both 0 at our starting point. So now we know what our phase angle is, and that's why we could use either sine or cosine for this function, because if we put sine of kx minus omega t plus a phase angle, we would get a different phase angle, but the starting condition would be the same, and the motion of the wave would be the same after that. Okay, so now we know our phase angle, so we'll go back to sort of our generic case. At any position in time, it's going to be the amplitude times the cosine of kx minus omega t plus 0. I'll just leave that out. So we found k and we found omega in part A of this problem, and the amplitude is given, so now we can just substitute in here. The amplitude, I'm going to convert everything to meters, 0.003 meters times the cosine of pi x minus 40 pi t. And that's the equation of our wave. In the last part of this problem, we're looking for the maximum transverse velocity of any particle. Transverse velocity. So we are given the y position of any particle as a function of time and x position in part B. Right? We've got the y position as a function of x position and time right here. So what we want to do now is figure out the velocity in the y direction, right? The transverse velocity. And that's going to be the rate of change of the position, right? The velocity in the y direction is going to be dy dt. And we know what y is as a function of t, so we can take its derivative. And the derivative of y, well, maybe I'll just write it over here. Yeah, I'll just go ahead. The derivative is going to be the amplitude times negative sine of pi x minus omega t times minus 40 pi. And we're looking for the maximum transverse velocity, and that occurs when the sine of pi x minus omega t is equal to 1. So V maximum is going to equal 0.003 times 40 pi.